Alright, so in this video I'm gonna be explaining another important article with the title Exploring Domain-Specific Features to Enhance Domain Generalization. For example, when we have a feature vector, some of it is, we can decouple it as domain invariant. The rest of that is domain specific. So this paper in 2021, by the way, this is the best company, AI company in Vietnam, and many great people are working there. So domain generalization aims to train a model from multiple observed source domains in order to perform well on unseen target domains. To obtain the generalization capability, prior domain generalization approaches have focused on extracting domain invariant information across sources to generalize on target domains, while useful domain-specific information, which strongly correlates with labels in individual domains and generalization to target domain, is usually ignored. So they propose meta-domain-specific domain invariant, a novel theoretically sound framework that extends beyond the invariance view to further capture the usefulness of domain-specific information. Our key insight is to disentangle features in the latent space while jointly learning both domain invariant and domain-specific features in a unified framework. The domain-specific representation is optimized through the meta-learning framework to adapt from source domains, targeting a robust generalization on unseen domains. We extract, label informative domain-specific, and then explicitly disentangles the domain-invariant and domain-specific representations in an efficient way without training multiple networks for domain-specific. For instance, consider the problem of classifying dog or fish images from the two source domains sketch and photo. While the sketch contains a conceptual drawing of the animal, the photo includes their taken picture within a background. In this case, sketch domain invariant is kept across domains, while domain-specific, for example, a dog in a house or fish in the ocean, will be discarded due to only existing in the photo domain. However, this background information, when present, could lead to an improvement of classification performance. For example, when we see the ocean, then it is more probable that a fish exists in the ocean rather than a dog or cat. And when existing background information is taken by pictures such as a house or ocean, it is crucial to take these backgrounds into account because the domain invariant feature extraction queue might ignore them by only existing in the photo domain. So in a typical domain generalization, a learning model which is only trained on the set of source domains, these source domains, without access to the unlabeled data. A feature extractor mapping is said to be domain invariant if the distribution of P of Q, this Q, is unchanged across source domains. Another definition, a feature extraction mapping, now this time is R, is said to be domain specific if for any I and J, the probability of I and J is not equal. So this is the graphical model A, which is, and the overall architecture, you see, that for a proposed MSDI, including domain invariant, so this is our domain invariant feature, this is our domain specific feature, which are disentangled using the covariance matrix. To push them to contain label information, these latents are integrated into a classifier F, which is optimized via cross entropy with the label Y, to make the model able to adapt specific information from source to unseen domain, while still remaining domain invariance information across domains. We additionally push Z sub S through a meta-learning procedure. So the paper aims to show that only learning domain invariant will limit the prediction. And then they carry on and work on theoretical analysis under information bottleneck method. That in A here, the learning procedure of minimal and sufficient label-related representation. In B, they explained in Theorem 1 where domain invariant-based methods provides an inferior prediction performance to our proposed method that incorporates both domain invariant and label-related domain-specific values. And in C, a case when the unseen domain has different X and Y, while domain invariant information is still stable across domains. And the assumption is that assuming that there exists a domain-specific representation which correlates with label in domain S1 such that the mutual information between Z sub S, that domain-specific part, and Y condition and X is same as mutual information between X1 and Y. A representation is said to be sufficient label-related representation, and Z sub is said to be minimal and sufficient representation if the argmax of our mutual information over G is Z. And the rest of that, this article is just a theoretical support. So we have discussed the main ideas of our proposed method. Here we discuss implementation. So in particular, our unified network consists of the following components. The domain is specific, domain invariant. This is domain invariant. This is domain specific part. We have a domain discriminator. We have a domain classifier. We have a classifier because we concatenate our invariant features with the specific features, and then we predict. So the domain invariant representation is obtained using adversarial training, in which the domain discriminator tries to maximize the prediction probability of domain label from latent Z sub I, while the goal of the encoder is to map the sample to the latent Z sub I such that D cannot discriminate domain of X. To extract domain specific, so this was for domain invariant because these are the parameters that you need. But for domain specific, again the same idea, the corresponding parameters. So the objective is expectation of D log D of specific over our feature R of X. Because R of X is just the latent variable of the domain specific features. The disentanglement condition between two random vectors cannot be solved by forcing their covariance matrix, denoted by cov, to be close to zero. So a detailed discussion of disentangled two representation is provided in appendix. Sufficiency of domain-specific and domain-invariant. So I explained this. Now we go to method training for domain-specific information. To encourage the domain-specific representation to adapt information learned from source domain to unseen, or sometimes they call it unknown target domain, we introduce the use of meta-learning, targeting a robust generalization. Note that the domain-invariant feature remains during the meta-learning procedure. In particular, each source domain, S sub m, is split into two subdomains, namely meta-train and meta-test. The domain-specific parameters and the classifier parameters are then jointly optimized. So the pseudocode for training and inference process of our proposed framework is in the algorithm 1. Each iteration of the training process consists of two steps. First, we integrate objective functions to construct an objective function like loss of individual invariant, domain invariant features, domain specific features, domain, and LT. So first we integrate the objective. The second step is to employ meta training to adapt task-related domain-specific. So they have meta training, meta testing, and meta optimization. So the output is just y using equation 4. Because this is a domain generalization paper, there is no, the target is unseen. So we go to individual domains and see the accuracy of that. For example, for the dataset office home, you see the method of this paper has this accuracy of 69%. So their model could capture the usefulness of domain-specific information. So for example, here they have source domains blue, green, and red. An unseen domain could be orange, but it discovers them. It can predict the unseen domain, which is this orange. And it's very interesting that the space of unseen domains is so big, it's infinite. And but it's like zero-shot learning, but with prior some learning for domain generalization. So it's very interesting. This dataset is very popular. The PAX stands for photo, art, cartoon, sketch.